Hello all. Now let's go to the second part of lecture 3. In the previous section we saw that that there is the first correction to the Drude's model, that was the wave nature of electrons, right? Now we say that now we take another step towards this corrections, where we say that the electrons are not fully free, but then the electrons reside in crystals, right? So electrons reside in crystals. So we'll take a small detour and then study crystals for some time, just to understand various crystals, the symmetry, the structures, as well as a mild introduction to the reciprocal space. I'm sure you guys must have seen this somewhere in your undergrad or any other courses, but then we'll just have a short introduction so that the next time we go into the band structure and everything, we hope everybody will be in the same page. Right. So let's start with crystalline solids. We go with crystalline solids because in the study of solids this is the easiest, because we assume there is periodicity. What is periodicity? Periodicity is translational invariance of the atoms. Okay. What do I mean by translational invariance is that if I have an atom at some point x, right, and I take a step of dimension of length a along the direction a, I reach another atom, right? And this is true for infinite steps that I take of size a along the direction a, as well as in the negative direction, right? And in 2D we can assume that the same thing can happen along b, along the direction b hat. This is along the direction a hat, and the same thing you can assume for 3D, right? This is magnitude c along the direction c hat. So one can actually represent these points using vectors as like this, right? Some m a vector plus n b vector plus p c vector. So what we mean is, this a is magnitude a and direction a hat, right? I take m being any integer numbers. So with any such combinations, I land up in a point where there are an atom. Another way to write this is summation of m, n and p is r. This is minus pc, right? This is pretty straightforward, right? For any value of r which is integral numbers of a, b or c, we get a 1, otherwise it's all zeros, and at each of the 1 point you have an atom, right? So basically what we say is that at each point in the crystal the surrounding atoms look similar, and this is what is called translation invariance, and this is what is called the periodicity. And this assumption, or this particular kind of solids, are the easiest to study with. So this was first studied in 1850 by a man called Bravais, and then he showed that depending upon the relationship between a vector, b vector and c vector, now the class of these solids can be divided into 7, depending upon if a vector, magnitude of a equal to magnitude of b equal to magnitude of c, and a dot b equal to b dot c equal to c dot a. This is one particular condition which we call as simple cubic. Okay. There are 7 different combinations like this, and he had independently named each one of them depending upon the independent relationships. And let us say if modulus of A equal to modulus of B not equal to modulus of C, and the second condition still being the same, is called a tetragonal, and so forth. Right. So so at this point, in addition to these orientations, he also identified that you can have two different kind of arrangements even in simple cubic. They are called as the body centered and face centered. So let us go and study some most basic atomic structures, so that the next time we say if somebody says a body centered cube or a face centered cube, they are not thrown aback, right? So okay, so now let us study the Bravais cubic system. The first one being the simple cube. The condition that we previously saw is A equal to B equal to C. All of them are having the dimension A, and x hat, y hat and z hat are the conventional Cartesian coordinates, all of them being perpendicular to each other. So you have the structure which is very similar to the ice cubes that we have, right? And there are very few elements which crystallize with this simple cubic format. But then if I take this simple cube and put an atom right at the center of this cube, right? Let us take, I'm taking this cube and then add an atom at the center, and that's what is drawn here. It is called as a body centered cube. So basically we have the same A, same B, but the C vector is not along the z direction, but then it is along the x plus y plus z direction, right? So we have an this is your A, and this is your B, and your C is actually along this particular direction and not this. And there are a few metals which crystallize in this particular orientation, which is called as a body centered cube. You have one particular atom at the body center. Metals like iron, potassium, barium crystallize in this particular structure. Another common structure is a face centered cube. A face centered cube is a cube that we saw before, and it has an atom in each of its face. So I have marked this as north, west, south, east, bottom and top, right? So these are the faces, and this can be seen here much easily. So I've taken this, and then you have this gray atoms in each of these face, including the top and the bottom. Now the simplest unit cells or simplest steps that you can take so that the arrangement do not change is in the A. If A is taken to be A by 2, you take half step in y and z, half steps in x and z is taken as B, and half steps in y and x is taken as this is C. So you can see that the lattice vectors are taken like this in each direction. So basically if I take like this, right? So one, so this is 1, this is 2, and this is 3. This is A, this is B, and this is C. So this is a face centered cube. Many metals crystallize in this particular structure. Most common ones are gold, silver, copper, aluminum, calcium. You must notice that the atomic arrangement here is one of the most close packed, right? Because you have more atoms per unit cell. So let us say I take this particular cell of each a simple cube that we saw before, and the number of atoms that you have here is thrice that what you see in a simple cube, right? In addition to this, there are other things. One is an hexagonal closed pack structure. So if A and B are not at 90 degrees but at 60 degrees, and C is still 90 degrees to A and B, it is called as an hexagonal structure. And you will have an hexagonal closed pack structure if you have two hexagonal lattices interpenetrating between each other. Right? So this is the first example of an interpenetrating lattice. So I have an hexagonal closed pack structure here. A and B are at angle 60 degrees to each other, and C is perpendicular to both A and B. C, the modulus C is not equal to A or not equal to B, but A and B are equal. Right? Now I take this and then put two of them on top of each other. So that's what you get here. Okay? So I have two lattices which are separated from each other. This is called an hexagonal closed pack structure. Another very common closed pack structure is an FCC with a motif. This is an important structure which is called as the zinc blend, because a lot of semiconductors crystallize in this form. So basically I have an FCC, the gray ones are the FCC that we saw before, and we have another red one kept with an offset. So I take the FCC, I take two FCCs and interpenetrate them with a particular offset. Right? So basically each atom has a twin attached to it very next to each other. This is called as an atom with a motif, and this particular example is called a zinc sulfide or zinc blend structure. A number of elements crystallize in this particular thing. If both the atoms forming these two FCCs which are interpenetrated, if they are the same, then you get what is called the silicon, germanium and the diamond, called a diamond structure. And if both of them are different, like gallium arsenide, indium phosphide, you have gallium nitride, you have indium arsenide, there is a whole bunch of semiconductors which crystallize in this FCC with a motif. So there is a particular information which is already being seen here. Right? One is the metals and the semiconductors have a distinct difference right here, right? Even before we go into the details, which we will go in the next lecture, but then you can notice that most semiconductors have this kind of an atom with a motif. Each atom is associated with another pair atom, and this is the origin of a chemical bond and so on and so forth, the covalent bond where atoms are completely bonded and such. Right? So basically this is the origin for such crystal structures. Now that we saw some very small and a quick introduction to the lattice structures, we did not go into the depth to understand all the possible lattice structures and the examples and such, because these are commonplace information in many textbooks, and of course you might have seen this in your undergraduate solid state devices course, so we do not go much into detail. However, there is one particular important feature that we have to see before we jump into the actual properties, that is called as a reciprocal space. So the information about the reciprocal space. The reciprocal space is actually a Fourier transform of the real space, and these are important because we already talk about periodicity, and when we talk about periodicity, it's quite natural to go into the Fourier space because it provides an easy handle to think about things which appear with a particular periodicity or particular frequency, so to speak. Right? So now let us have a very short introduction to the reciprocal space. And we saw that the reciprocal space is a Fourier transform of the real space. So we all must have come across this particular definition, right? So if we have A vector, B vector and C vector as real space unit vectors, then the reciprocal space is thought to be 2 pi or 2 pi b cross c by a dot b cross c, right? And so on and so forth. We would have taken these things as reciprocal spaces, reciprocal space vectors, right? Let's say I have a is like this, b is 2 pi c cross a by a dot b cross c. Now let's understand why is such a definition necessary. If any of you have any further any different way to understand this, I'll be more than happy to look at it. But then this is another interesting way to look at why one should define a reciprocal space like this. The main reason is that the reciprocal space is a Fourier transform of the real space, right? And we saw that the real space can be represented as f of r is summation over m n comma p delta cube r minus ma minus nb minus pc, where m, n and p are integers and a, b and c are the unit vectors, right? Let's take for instance the simplest simple cube for so the reciprocal space, let us say I call it f of k, is integral minus infinity to plus infinity f of r e power minus I k dot r dr, right? So now if I put this our definition inside, I have delta cube summation m n p r minus ma minus nb minus pc, right, into e power minus I k dot r dr. Now because these are linear operators, I can put the summation out. Integral, this has to be a triple integral, right? nb minus pc e power minus I k dot r dr, right? And this is what we defined. This is what we defined as capital R in the previous place, you remember, right? And an integration of an integration delta of x minus a dx is f of a, right? F of x, right? So I have m comma n comma p e power minus I k dot capital R, right? This is the Fourier transform of the delta train that we had in the real space. Now let us say this k, okay, I represent this k as some vector, right? Ka a vector plus kb b vector plus kc c vector. This a, b and c for now are random vectors, okay? Capital A's and the other ones are small a's. So this k dot r, this inner product, is actually ka into m a vector dot a vector plus ka into n a vector dot b vector plus so forth, right? Plus kb dot n b vector kb dot n b vector dot b vector plus so on and so forth, right? This is such a huge expression that we just cannot resolve. Now this is where the actual definition of the reciprocal space comes in. So here, if right, if we have a vector G, right, which is defined as KAA plus KBB plus KCC, and this A vector is our previous definition, right, is B cross C by A dot B cross C, and B is to pi C cross A dot B cross C, and C is to pi A cross B C dot A dot B cross C. Right? So if we have something like this, then it's easy to see that if I have G dot R, is all the other terms, all the non-diagonal terms will turn to 0, and only the diagonal terms will remain, and this will be 2 pi Ka dot n plus Kb dot n plus Kc dot b, right? And e power G dot R is unity. So let's go back to our actual definition. So given this particular periodic arrangement, now we know this e power minus I k dot R, right? Now this is simply 2 pi by A, 2 pi by B, 2 pi by C, summation delta of k minus m into 2 pi by A into delta k minus m into 2 pi by B into delta k minus n p into 2 pi by C. And this you can write as 2 pi cube by omega being the volume in the real space, unit cell, delta cube k minus g. So the delta train, the 3D delta train that we saw in the real space is converted into a delta train, a 3D delta train in the reciprocal space. However, the volume of the unit cell in the reciprocal space is actually 2 pi cube by the actual volume in the real space. And similarly, we have taken the definition of the reciprocal space to be 2 pi by each vector in the reciprocal space to be 2 pi by A times the real vector space, right? So this is the origin for the definition of the reciprocal vectors, and the most important part is here, right? So the reciprocal vector and the real vector shares this particular relationship such that any reciprocal vector, let's say if G is any reciprocal vector, and R any real space vector, then e power I G dot R is 1. Okay. Now, in addition to this, there are other numerous important properties of a reciprocal lattice vectors. I will just name one which is very important for our current discussion, that for every G, let's say if G is any reciprocal lattice vector, for every G, right, there exists a family of plane separated from each other by 2 pi by g1, where g1 is a vector parallel to g which is having the smallest reciprocal lattice length. I repeat, for every reciprocal lattice vector g, let us take let's take this is our 3D reciprocal lattice and I have a reciprocal lattice vector g. Right? I am saying for every point g, okay, there exists a family of planes in the real space which are separated by, this is g1 along g parallel to g with the smallest reciprocal lattice length. Right? Now later on in the further lectures, we will see that we will use such features, and there are other features which we will explore in the homework, which you must have previously seen in other in your undergraduate solid state physics and so forth. So we stop here and we'll continue the next lecture. Thank you.